Okay, let's go and get started today. Last time we talked about grammars, and today we're going to talk about derivations. And derivations are a topic that's related to grammars. It's something you do with grammar, so let's go and take a look. All right, so first thing here to quickly review, last time we talked about context-free grammars, and those are a new way that we hadn't seen before of defining languages in a formal way. And that method, context-free grammars, can actually define all regular languages. So it can do everything that a DFA, NFA, or regular expression can do, but it could also describe some languages that were not regular. So it could get us outside of the regular languages into what are called the context-free languages. And the context-free languages being a broader set, well, let's just do a quick review of what a context-free grammar is. So a context-free grammar is defined by a quadruple, and where consisting of V, T, S, and P. So in other words, this formalism has, and notice I'm not calling it a machine this time because it's not really a machine like a DFA was. It's a kind of a formalized way of defining a language that has these four parts. So the first part, V, is a finite non-empty set of objects called variables. T is another finite non-empty set of what we're calling terminals. And if you remember what the terminals are, those are like the symbols from our alphabet. And variables are kind of like these things that are used internally by the formalism to eventually get to terminals. S is a special variable called the start variable. And notice that S has to be an element of V. It has to be one of the variables. So we identify one of the variables as the start variable. P is a finite non-empty set of what are called productions. And those productions look like this. We have X producing Y. And in a context-free grammar, X is a single variable, so we always have a single variable producing some string of 0 or more variables and terminals on the other side. And the way that the machine worked is you identify a variable, you replace it by one of the right-hand sides, so it's like cut the variable out, paste in whatever's on the right-hand side, and repeat that until we only have a string of terminals, and then that string is in our language. Now, quick review, context-free grammars get us outside of what we can do with regular languages. So context-free languages are outside of that, but notice there are no regular languages that are also not context-free. But there are some context-free languages out here that are not regular. Okay, and the language that's defined by a context-free grammar, informally, it's the language of that grammar is the set of all strings in T star. In other words, all strings of either lambda, so 0 or more terminals, but it's only terminals, that can be produced by starting with a start production, then applying productions of the grammar. So if we have a context-free grammar that looks like this, S produces the symbol A followed by variable S, or just the variable A. And then we have variable A producing symbol B from our alphabet, followed by capital A again. So call back again, or just B. What is the language of that? And so you'll notice that what this does is S can go directly to this production variable A, which can then either make a B and stop. So the smallest string we could get from this would be just a B. But I could also loop here and make a B followed by another A, B followed by another A, make any number of B's and then stop. So this A production here, if we look at that, that's creating one B or more B's. So this is one or more. So this is a lot like B plus. Now what about S here? Well, that could skip over directly to A and generate no symbols, or it could make a string of A. So this is kind of like A star. So if we think about that, that language is regular. And what does it look like? Well, the regular expression will be A star B plus. So here's the A star part. And then once that moves on, we get at least one B, but we could get more B's. So there's one or more B's, which is B plus. Okay, now a derivation. What a derivation is it's a sequence of productions that were used to produce a particular string. So in other words, if we have some string that's in the language, there have to be some productions that can be applied or used in some order. So in other words, we're going to cut and paste, cut and paste, cut and paste, cut the variable, paste the right-hand side, cut the variable, paste the right-hand side, or we're going to do that some number of times. So what a derivation is, it's kind of like a tracking the sequence of what was used to cut, what variables were cut, what was pasted in order to get to that particular string in the language. So every step in the derivation has to be some valid step where we're taking a variable that's on the left-hand side of a production and replacing it with the right-hand side of the production. All right, so let's write out a derivation. So here's our example from earlier, that same grammar that we had that was A star B plus, linear grammar. And you'll notice this is right linear. And if we look at this string AABB, how could we use these productions to get that particular string? Well, looking at that, we're going to start with S, and then S has two choices. It either goes directly to A, or it does this one. In this case, we're going to use the first one, so little a S. So what that's going to do is we're going to use this variable S, we're going to replace it with a S. And each step of this, I'm going to highlight the variable that was used and then what it was replaced with on the right-hand side. So notice this replacement, S producing that, came directly from this production over here. Now we're going to replace S again, but this time we're going to pick AS again, so that same production. But notice that S that was in that string here gets replaced with the right-hand side again, the AS from over here. And now we're going to replace S again. This time we're going to use S produces A. So S produces A. And now we have that A that's going to be replaced, and it either has to be replaced with this or this. It's going to be replaced with BA, so A produces BA. And then that A is going to get replaced again. A produces B. And now we have a derivation. So we have that string that we were trying to find the derivation for. And notice this is the sequence that we went through to get there. So we found a derivation for that string. Now, a couple of other pieces of terminology here. An arrow with a star after it, or an arrow with a star over it. And this is kind of farther away than it should be. It should be right on top of it. But the stupid word processor, that's how it did that. So this arrow with a star over it denotes 0 or more steps along a derivation. So in other words, S followed by 0 or more productions or applications of steps along our derivation gets us to that. It also gets us to that, or that, or that. It can get us to a lot of different things. But this is just kind of a shorthand for cutting out parts of this derivation. So S, instead of listing all of them out, you could put a star over that and say S will eventually get to that, if there really is such a derivation. Now, leftmost and rightmost derivations. That in a context-free, or in context-free grammars that aren't linear, sometimes you'll wind up with two variables on the right hand, or in part of a step along a derivation. And that means we have a choice as to which one to expand during that step. In other words, if we have two variables, we could choose to do the first one, the second one, or really any of them. And so what a rightmost derivation is and what a leftmost derivation is if you always replaced, for example, the leftmost symbol, the leftmost variable, in each step of a derivation, then that derivation is called a leftmost derivation. If you always replace the rightmost variable in each step of a derivation, then that's called a rightmost derivation. And let's go and take a look at an example of that. So here, for example, is the grammar. S produces A, A, B. Notice this is not linear because we've got two variables, one on the left, one on the right. And we have A, A. And then the string that we're trying to find the derivation for is A. So notice, let's start the first one here. So S, there's no choice. We have to use that variable because that's all there is. We replace that with A, B. But now we have a choice. Do I cut and paste the A or the B? Do I choose to expand A or B? And in this case, we're doing a leftmost, so we're going to use the A. So A gets replaced with lowercase a. And now we don't have a choice, so now we're going to replace the B. B gets replaced with AA. And then now we don't have a choice, so A gets replaced with A. But notice, is this a leftmost derivation? Yes, because when I did have a choice, I chose the leftmost variable to do the replacement on. When I didn't have a choice, it doesn't matter. It's both leftmost and rightmost step when we don't have a choice. But if I do have a choice and I always choose the leftmost symbol, it's a leftmost derivation. And conversely, here's a rightmost derivation for that same string. So S produces AB. This time we choose the B right here. Replace that with AA. Now we have another choice in this step. Which A do I do? The first one or the last one? In this case, we're doing a rightmost derivation, so we pick the one at the end. We replace that, and now we don't have a choice and replace that. So notice both of these are derivations. So this has two different derivations for this string. And really, there are more than two derivations. I could have picked the rightmost one here and the leftmost one there and had a different derivation again. Now, the way we indicate those leftmost and rightmost is with these symbols here. So an arrow with LM underneath it, or an arrow with a star over it with LM underneath it. LM stands for leftmost. So this is a leftmost step along, single step. This is 0 or more leftmost steps along a derivation. And then rightmost is the same thing, but with RM underneath it. Okay, so now back to the definition of a language. We had an informal definition earlier. So formally, the language of a grammar, G, defined by the tuple VTSP, is, so the language of that grammar is all strings W such that W is only terminal, so 0 or more terminals, and S, starting with S, applying 0 or more steps along a derivation. It doesn't matter if it's leftmost or rightmost here, we can get W. So in other words, all strings that we can get by starting with S as long as they're only terminals. So again, in English, the language defined by grammar G is a set of all strings of only terminals that can be produced by starting with the start production S and applying 0 or more productions in P. Now, this English one is a little bit confusing. It says strings of only terminals. That can also include lambda. Notice because star is there. So all strings, maybe it should say all strings of 0 or more terminals that can be produced by starting with the start production S. Okay, and that brings us to another definition here, the definition of what's called a sentential form. And what a sentential form is, it's any string produced as an intermediate or final string along a derivation is called a sentential form. So in other words, when we looked at that chain of things that we could get back here, every one of these is a sentential form. So the ending is a sentential form, the beginning is a sentential form, everything in between is a sentential form. So sentential forms are anything that we can get along that derivation. So in other words, any string alpha that's an element of V unit T star such that we can get to that string by starting with S is a sentential form. So if S is only, if we only use leftmost applications of productions, so leftmost steps along a derivation, then alpha is called a left sentential form. If we only use rightmost applications of productions or steps along a derivation, then alpha is considered a right sentential form. So going back a couple pages here, these are all left sentential forms. These are all right sentential forms. And just because some of them overlap, like A, and S, those appear in both of these, that means that those are both a left and a right sentential form. Okay, so we know what sentential forms are. We've defined those. We know what the difference between left and right sentential forms are. We know what a derivation is. So now let's look at this concept of what's called a derivation tree. And what a derivation tree is, it's a way of showing a derivation that's independent of the order in which the productions were used. And those derivation trees can be important because, for example, while the order might matter sometimes, in this particular case, it's important here to note that the derivation tree does not show which of these gets expanded first. So S produces AAB. And in this particular case, we could, if we're doing a left sentential form, A would get expanded first. And then if we get a right sentential form, B gets expanded first. So A, B. doesn't matter. It just A is eventually going to go to A, B is eventually going to go to A is going to go to A. So in this case, the derivation tree doesn't show which one we did first. It just shows what they eventually did. And that can be useful because it can tell us whether or not the derivation is actually different or really the same. And so, for example, that brings us to this concept of what's called ambiguity in a grammar, or ambiguous grammars. And a context-free grammar is ambiguous if there exists some string W such that W has more than one derivation tree. And S produces ASB or SS or lambda in this case. This is a really simple grammar. It's only got 3 productions in it. AABB. S produces ASB. S produces ASB. S produces lambda. So this is one derivation tree for that. So notice if we follow an in-order viewing of this tree, what gets produced first is A, and then right after that is the second A, and then right after that is this lambda, and then right after that is B, and then right after that is B. So there's our AA, nothing, BB getting produced. Now, is there another derivation tree for this particular context-free grammar for that string? Well, yes, here's another one. S produces SS, this S produces lambda, and then this side produces the same thing that we had over here. And you'll notice there are 2 distinctly different derivation trees for that same string, so this is actually an ambiguous grammar. There exists some string, in this case AABB, that has more than one derivation tree. And in fact, this particular string has an infinite number of derivation trees. Like off of this S, I could produce SS, and each of those could produce lambdas, or another S and another SS, and those could produce lambdas. Or up here, I could grow this as much as I want and have things collapse down to lambda, and then eventually have one of those branches of S do what we did here. Or this S could produce SS. There's really an infinite number of ways, derivation trees, we could create these things. So there are an infinite number of trees for AABB. And in this case, the main thing to note here is that there's another class of ambiguity here called an inherently ambiguous language. And that what an inherently ambiguous language is one for which there is no way to create a context-free grammar that is not ambiguous. So in other words, there are some languages that are just inherently ambiguous. And that means that the important part about that is that if that language could never be converted into a grammar that is unambiguous, then the language itself is inherently ambiguous. Now, question to ponder, is this language that we have here inherently ambiguous or just ambiguous the way we have it written? And I want you to think about that. Maybe I'll put that as a quiz, or maybe it'll be a bonus at some point, and I'll ask that again. But think about this language for a second and note that this is a useful language. That if you think of A's as open parentheses and B's as close parentheses, then this language produces the set of all possibly matched nested parentheses. So open, close, open, close, open, close, open, close, open, close, open, close. So is there a way to create a grammar that represents that language of all possible sets of nested parentheses that is unambiguous? So think about that, and we'll cycle back to that a little bit later. Okay, so that's all for today. Relatively short lecture. Go ahead and make sure you work on your previous context-free grammar assignment. Make sure you ask questions if you have them and get back to me on that. And other than that, that's it for today. And next class, we're going to dig a little bit further into context-free grammars and looking at how to manipulate them. So just like we could with regular expressions where we had algebraic properties, we don't really have algebraic properties of regular expressions, but there are ways to manipulate them through substitution and through factoring things and to put them into different forms. And that could be useful, for example, saying taking a language like this, a grammar like this that's ambiguous, and turning it into something that's not, or making a grammar smaller, simplifying things. So anyway, we'll look at that next time, and that's all we're going to do today. So go back, look at your assignment, and work on that. And I'll see you shortly.